So the first problem we have is a quadratic inequality. So we're going to do this in two general steps. We're going to find our boundaries, and our boundaries are what make the two sides equal. When we have linear inequalities, for example, y is less than or equal to x plus 4, we put a line on the boundary and then we test to see which side works, which side of that works. We can do the same thing here. We want to find out where does this change from being greater than to less than, and that's going to be typically where it's equal. And then we do a test to see which side of the boundary is good, which side is not, which side works, which side doesn't. And that's going to keep us from having to graph this and everything. So let's change this to an equation. And then if we solve this equation, it's quadratic, so let's get everything on one side. So let's subtract x from both sides. Let's add 3 to both sides. So those are gone. So we get x squared plus 4x minus 12 equals 0. That factors to x plus 6, x minus 2. And if we set each factor equal to 0, if we set each factor equal to 0, we get x equals -6 and x equals 2. So those are the two values that make the left and the right side equal. So we only have one variable. There we go. We only have one variable, so we don't have to have a grid. We can just use a number line. So -6 and 2 are where the left and the right sides are equal. Now we want to figure out which sides are going to make the inequality part true. So let's copy down. We got x squared plus 5x minus 15. The screen's acting up on me. X squared plus 5x minus 15. We want to see when is that going to be greater than or equal to x minus 3. Excuse me. So we're just going to test a point in each interval. So let's put in a -8. That's in that interval. A 0 is here, and a 4 is here. So see which intervals work, which don't. So if we put a -8 in, -8 squared is positive 64. 5 times -8 is -40, minus 15, and let's see if that's going to make this work. -8 minus 11, or minus 3 is -11. So let's see, this is 24. 24 minus 15 is 9. And that's a true statement. So we're going to highlight this side. All right. If we put a 0 in, 0 squared is 0. 5 times 0 is 0, minus 15. And let's see if that's greater than or equal to 0 minus 3. So we get -15 is greater than -3. Remember, the bigger numbers are the farthest to the right on the number line. Well, that number is farther to the right on the number line, so that's not a true statement. So that means the middle interval does not work. All right, now let's test 4. So if we put a 4 in, we get 4 squared. 4 squared is 16. 5 times 4 is 20. Minus 15, and let's see if that's going to work. Putting a 4 in, so 4 minus 3 is 1. So we get 36 minus 15, which is 21, and that's a true statement. That's true. So we are going to highlight this. Now keep in mind, our problem is we're looking where is it greater than? It's greater than in the blue section on the left and the purple section on the right. That's where it's greater than. We also include where it's equal. It's equal here and here. So we put on a number line, we put brackets at those. So as an interval, we go from negative infinity to -6, and we go from 2 to infinity. So solve it as an equation, and then testing each interval lets us know what intervals work, what don't. Now if we try this one, let's change this to an equation. If we rearrange this, we would have -x² plus 6x minus 9 equals 0. If we multiply both sides by -1, we would get x² minus 6x plus 9 equals 0. That factors to x minus 3 times x minus 3. If we set each factor equal to 0, we get x equals 3 as a repeated 0. So we get x equal 3 two different times. One variable, so we can put it on a number line, and 3 right here, that's where the two sides are equal. If we plug a 3 in, it makes the left and the right side equal. We want to know where is it less than? So we're going to pick a test point in each interval. And it could be any number as long as it's inside that interval. So we're going to take our original problem and we're going to put in a 0, and we're going to say, does 0 work? And then we're going to put a 5 in, say if 5 works. So if we test a 0, 6 times 0 minus 9 minus 0 squared, let's see, is that less than 0? Well, -9 is less than 0, so that works. So that means 0 is a solution, so everything in that interval works. Not just 0, but everything in the interval with 0. Now let's test a 5. If we test a 5, we get 6 times 5, which is 30, minus 9 minus 5 squared. Well, 5 squared is 25. And let's see if that's less than 0. Well, this is 30 minus 9 is 21. 21 minus 25 is -4, which is less than 0. So in this case, numbers on that side work as well. So let's look. Everything to the left of 3 is okay. Everything to the right of 3 is okay. But what about 3? Do we include where the two sides are equal? Well, no, we don't. On this one, we only include where it's strictly less than, which is this side and this side. We do not include where it's equal. So on a number line, we would put either an open circle there, or we would put parentheses going each way. Everything from -infinity approaching 3, and everything approaching 3 going to positive infinity. Everything except 3 is going to work for our problem. Now think about if that would have been turned around, if it would have been greater than. If it would have been greater than instead of less than, this wouldn't have worked. This wouldn't have worked. And if we didn't include where it's equal, that wouldn't have worked. So nothing would have worked. If we were doing greater than, there's no number that would make that a true statement. But since we're doing less than, every number works except 3. So this is a good example of why we need to test each interval. We can't just simply say, well, one interval works, so the one beside it doesn't. That's not always true. Sometimes adjacent intervals both work, sometimes neither work. So find the boundary. Once you get the boundary, test both sides. Now this one is a little trickier because this one doesn't factor directly. This has 4 terms without a common factor, and factor by grouping doesn't work. So we're going to have to factor this to find the numbers that go into our number line using synthetic division. So this is a good review. So to find out what potential numbers we should even try, we need factors of 10 divided by factors of the leading coefficient. So we get plus or minus 1 over 1, 2 over 1, 5 over 1, and 10 over 1. So those are our potential rational zeros. So let's pull out synthetic division, and let's see if we can find some zeros that work. So I'm going to start with a 1 and do synthetic division. And the very first one we try works. When we plug 1 into this polynomial, it makes it 0. So that means x minus that number is the divisor or is a factor, and we can rewrite it as x minus 1 times the quotient, which is our number, x, and x to the second. So 1x squared minus 7x plus 10. So that's the left side of our equation, the other side is 0. We're looking for what makes our equation equal to 0. All right, we can factor the quadratic as x minus 2, x minus 5. And then if we set each factor equal to 0, we get 1, we get 2, and we get 5. So those are our zeros. 1, 2, and 5. So we need to test a number in each interval. So we could test 0, we could test 1.5, 3, and we could do 7. So we're going to take each number, plug in to our original problem. We always want to go back to the original, which is x cubed minus 8x squared plus 17x minus 10, and we're looking for when is that less than 0. So if we substitute a 0 in, we would get 0, 0, 0 minus 10 is less than 0, which is true. So we would highlight this. Now, without taking my calculator out and doing every single one of these, if we plug a 1.5 in, which we could do this with synthetic division, the next one doesn't work, the next one does, and the next one doesn't. So if we plug numbers from each interval in, the first and the third intervals are going to work, the other ones aren't. Notice we do not include where it's equal, so we don't include 1, we don't include 2 or 5. If we did include where it was equal, we would have a bracket at those. So if we write this as intervals, we go from negative infinity to 1, and then we go from 2 to 5. And those are the values for which our inequality holds true. Now, the last problems that we're going to look at are rational inequalities. And we're still going to do the same thing. We're going to find our boundary points, and we're going to do our test points. So boundaries on the previous problems were where we were equal. But when we have something that's rational, we also have another type of boundary, and that's when we're undefined. Why undefined? Because if we have a fraction, we can't divide by 0. So anything that would make the denominator 0, we're not allowed to have. So that creates a break. Even if every other number worked for this problem, if it makes the denominator 0, then it's undefined, which means it can't possibly be part of the solution. So let's start there. Let's look for our boundaries, and the first boundary that we're going to look for is where it is undefined. So we're going to take the denominator and say, what would make the denominator 0? And the reason for that is it would make it undefined. So if we take 2 away from both sides, and if we divide by 5, we get negative 2/5 is what would make us undefined. Negative 2/5 would make this undefined, so we can't have a point there. The other type of boundary would be where our two sides were equal. So change it to an equation and solve the equation. Well, if we have a fraction and we want to clear the fraction, the opposite of dividing is to multiply. So multiply both sides by 5x plus 2. So if we have a 5x plus 2 on the top and a 5x plus 2 on the bottom, those cancel. So we get negative 4 over 1. On the other side, 0 times anything is 0. Notice that doesn't match up. That gives us a false statement. What does that mean? That means the two sides are never going to be equal. There is no solution that makes the two sides equal. So in our case, we only get one boundary. We get the boundary where we are undefined. So if we draw a number line, we have a boundary at negative 2/5, and that's the only boundary we have. And I'm going to make a note because that's the boundary of being undefined, which is different from a boundary of being equal. So let's take our original problem. Let's not draw that big line like that. So our original problem, and let's see which side works. So numbers to the right, we could use a 0 because that's to the right. We could use a negative 4 because that's to the left. Any number would work. Just pick some number in each interval. So let's try negative 4 first. So if we put a negative 4 where we have an x, we have 5 times negative 4 plus 2. Let's see if that's less than 0. So we have negative 4 on top, negative 20 plus 2, which is negative 18 on bottom. Negative over negative is positive, and that would reduce. But whether we reduce it or not, 2/9 is not less than 0. Negative over negative is positive, so that does not work. Now, if we plug in 0, let's see if plugging in 0 for 0 works. So if we replace x this time with 0, we get negative 4 on top, 0 plus 2 on bottom. So we get negative 2, and that does work. So that means since that works, we're going to highlight that interval. Now, our problem says we don't include where we're equal. Well, we weren't equal anywhere. Where we're undefined, we never include a number that makes us undefined as part of our solution. So we have to put a parenthesis here to show we don't include negative 2/5. So our interval goes from negative 2/5 to positive infinity. All right, let's do one more. So if we start with our boundaries, we have two fractions. If this denominator is 0, that's a problem. So let's see what makes that 0. And if the other denominator is 0, that's a problem. So what makes that one 0? So x equals 5 and x equals -9 are the two numbers that make us undefined. We're not allowed to let x be 5 because we would get a 0 on bottom. Same with a -9. Now to find the other type of boundary where we're equal, let's change the two sides or change it to an equal. So x minus 1 over x minus 5 equals x plus 5 over x plus 9. Whatever makes this true is the other type of boundary, the boundary of equality. So to get rid of the x minus 5 on bottom, we would multiply both sides by x minus 5. To get rid of the x plus 9 on bottom, we would multiply both sides by x plus 9. So we would have x plus 9 times x minus 1 equal x plus 5 times x minus 5. So we want the parentheses to go away, so we would want to distribute that, combine like terms, so we would have x squared. We would have minus x plus 9x, so that would be 8x. 9 times -1, so minus 9. Then we have x squared minus 5x plus 5x, which would cancel, minus 25. So notice, if we subtract x squared from both sides, to get our x squareds all on the same side, actually all the x squareds are going to cancel. So we would have 8x minus 9 equals -25. Add 9 to both sides, which would make a -16. Divide both sides by 8, and we would get -2. So that number is what would make the two sides equal. So we have three boundaries. We have 5, -9, and -2. 5, -9, and -2. -2 is where we're equal. These other ones are where we're undefined. So then we would want to go through each interval and test values and see in which intervals do numbers work and which intervals do numbers not work. So we're going to take our original problem, x minus 1 over x minus 5 is greater than or equal to x plus 5 over x plus 9. And then we're going to plug in each of our test points. So if we plug in a -10, we get -11 over -15. On the other side, we would get -5 over -1. So we would get 11/15 is greater than or equal to 5. Well, that's not true. 5 is bigger. So that doesn't work. Oops. That doesn't work. If we go back and we plug in a -7, we get -8 over -12, -2 over 2, so we get 8/12, which can reduce. It's greater than or equal to -1. That's true because 8/12 is positive. So we're going to highlight here. If we plug in a 0, we're going to get -1 over -5 is greater than or equal to 5 over 9. So 1/5 greater than or equal to 5/9. That's not true. 5/9 is bigger. So that doesn't work. And then lastly, we're going to try a 6. So if we try a 6, we get 5 over 1. 11 over 15. 5 is bigger than 11/15. That works, so we highlight this. So we have to be a little careful. We include where it's greater than, that's everything that's highlighted. We include where it's equal. Well, where is it equal? It's only equal at -2. So we include there. We do not include -9 because that makes it undefined, and the same thing with 5. We don't include 5. Only where it's equal. So we go from -9 to -2, bracket, and then 5 to infinity. So we did it very similar to the other ones. We found our boundaries, but if it's undefined, it's a parenthesis. If it's equal, since we do include where it's equal, it's a bracket.